Welcome to Digital Design and Making 101 workshop series, and today is topic 4, where we're going to be doing a deep dive into 3D printing and additive manufacturing. I'm just going to start with a couple of stories first. This is Paige Whitehead. She has graduated now, but was a third-year microbiology and environmental studies student who created a biodegradable glow stick. Paige took our 3D design and print workshop so that she could work on a prototype cap for her glow stick. So as a proof of concept, she started with a 3D printed cap before moving on to manufacturing a metal cap, which is what she wanted to do a little bit further down the road. And at this point, she's won several awards, and you can check out her business there at LuxBio. I think she's been on Dragon's Den too, which is kind of cool. So another example, and this is 3D printed prosthetics here at UVic. Nick Dekchev of the engineering department here at UVic got into the, I'm not sure the story behind it, but created some software so that they could create low-cost prosthetics for amputees originally in Guatemala, and then have moved into places in other parts of the world. And while a prosthetic hand in Canada costs about $12,000 and advanced models cost as much as $70,000, Nick leads a project that has created hands for only $200 using 3D printers and spools of plastic, which again is pretty cool. We can create a whole bunch of different things with 3D printers. We can design things, we can scan things, we can use designs that other people have made, and you can see there's a broad range of things that we can do. These are the 3D printers that we have in the Digital Scholarship Commons. We've got our newest printer is the Bamboo X1E. It's a little bit smaller than the Ultimaker 5S, but it is very, very fast and high quality. The 5S is our largest printer, and we have 3 of them. They can handle quite large print jobs. It's not quite as fast as the Bamboo, but the quality is quite high. And again, it'll accommodate those bigger jobs. And then lastly, we have 2 Ultimaker 3s that about the same. They are the same speed as the Ultimaker 5, but just a smaller print area, but still very, very useful. So just in terms of how we move from design to print, so we design our model first in our case, we're using TinkerCad or Autodesk Fusion. Then the next step would be to load the model, the STL file into Cura, and then we can, and this is printing software for 3D printing, and we can get a sense for how long it's going to take, how much material it's going to use. This isn't a requirement to load it into Cura, but it can be quite helpful for you to get a sense for what different settings will do in terms of material being used or print time. And then print it. This is an example of a 3D printer. This was one of our first 3D printers, which is no longer running, but all the 3D printers have common features. The first one is the build plate, where it starts to print jobs, and again the build plate would move up, so it's right almost touching the extruder, and then the extruder will do its thing on one layer, then the build plate will just drop down a tiny bit and do another, and the filament or the plastic feeds from the back of the printer up and around and through the extruder, where it gets heated up to over 200 degrees Celsius. And there's a little display up top that gives you a sense for what's going on with the print job. Importantly, if you're managing multiple print jobs, how long it's going to take for the current print job to finish. So the type of printing that our printers use is called fused deposition modeling. And let's say we've got a model of an elephant. The slicer software, or in our case Cura, will take the model and figure out where all the different layers are that it needs to put down filament to make the model. And if you zoom in on a model or you get a magnifying glass on a 3D printed model, you can see the little layers on the model. It can be hard to see if you're not looking for it, but they are there. So the filament from a spool will come up, it'll get sucked into the print head, and then it's heated up here and then extruded layer by layer. And the build plate, like I mentioned before, will drop down. The process is quite cool to see, but it is really slow, and you'll get a sense for that when we're looking at the printers in action. One thing to know is that sometimes or not sometimes, it can be difficult to get a physical part that you've got to interface with a part that you've designed and printed, because sometimes things will be a little smaller or a little bigger, usually a little bit smaller. So if you've got a hole that you've got an axle to go through, you might need to do some experimentation to figure out how big you actually need to make it, because the size that you think it should be numerically will probably be a bit smaller for a couple of reasons. If we look down here, there's a fillet or a rounded edge. That rounds it, but if you don't do a fillet, you get a little bump on the edge, and that little bump will make it smaller. Like, for example, you've got a hole in a model that you need to put something through. That fillet will make it so it's smaller than you expect, and the thing likely will not fit unless you make the hole a bit smaller. Same thing with corners. A chamfer or a fillet, again, help get rid of those little bumps that you get on corners. You can't see the bumps, but they are there, and you'll notice it when you're trying to put things together. So here's a video of a 3D printer in action. So I'll mute the volume here. It's sort of mesmerizing sound, but as you can see, it's going around the outside edge of the model, and then it'll fill in a little bit at the top. And as I mentioned before, this is really cool, but as you can see here, it is very slow. So it's the type of thing you just start the print job and then come back the next morning if it's a big enough print job. Another thing to be aware of is supports. So if you've got an object like this, let me get my laser pointer out here. We've got a Triceratops there, the tail, the head, the belly all overhang. So what you need to do is enable supports so that the slicer software, in our case Cura, puts supports under it. Otherwise you'll get a really ugly, the tail won't form properly for a long time, and the head and other things. So you do need to put supports. And if in doubt, you want to add supports, because the slicer software is smart enough to know that if the model doesn't need supports, it won't put any in. Printer orientation can also make a difference. This is a table in two different orientations on the build plate. Might not be obvious to you, but the one on the left will print more quickly and be of higher quality than the one on the right, and we'll see why in a second. This one, it prints straight on the build plate, the legs go up, whereas this one, it had to print a whole bunch of supports that you're going to have to break off, and be mindful not to break the legs as you're pulling off the supports or breaking the supports off. So that may not mean much to you now, but just trust me, breaking off those supports will make the underside quite rough, whereas this one will be, this is definitely the preferred way to handle the print job. Another thing is infill and shells. Shells is how many outside layers to the model. So this is a 2 shell. It's kind of hard to see, but there's two layers to the outside, and then a 10% infill. This one here, you can see the outside edge is thicker. That's a 5 shell, and then a 5% infill. And then this one is 10 shell and 20% infill, because it needs to be really strong for some reason. You know, if you are wondering why you wouldn't just go for the stronger one, it takes quite a bit longer and is quite a bit more expensive, because you're paying for the cost of the material, and there's just a lot more material here. By default, we print the print jobs will be 2 shells and a 10 or a 15% infill. So we have a few different filaments that are available to you. By far the most common one is PLA, polylactic acid, and it's derived from renewable resource like corn, cassava, sugarcane, and it can be broken down in industrial composting settings. And if you just leave it outside in the elements, it'll take several years to break down, but it will eventually break down. Another one is PVA. It's closely related to PLA, but it is meant to dissolve, and it's meant to be a support filament, so that instead of breaking things off of the breaking supports off that leave jagged edges on the model, this will dissolve away and works quite well. The only drawback to it is that the PVA is twice as expensive as PLA, and you do have to spend quite a bit of time. You know, a big one like this, you'd need a big bucket and a weekend for most of that to dissolve. Next one I'll talk about is PETG. It's stronger than PLA and more weather resistant. So that is good. It's the same price as PLA, but it tends to string a little bit, which isn't the prettiest thing in the world, but it can be quite helpful in use cases where you need something that's stronger and more weather resistant than PLA. Last one is TPU95, and this is a flexible type of material, and it works quite well. It's costs twice as much as PLA. Oh, I forgot to mention, PLA costs 10 cents a gram, PVA 20 cents a gram. TPU95 is also 20 cents a gram. And the PETG is 10 cents a gram, the same price as the PLA. So, yeah, so let me know if you have any questions about that, of course. So this is what Ultimaker Cura looks like. This is a model that we've got in the Digital Scholarship Commons that I can show to you. We printed it in a vertical way so that we don't have to use supports. And I'll go over the settings in the class with you folks, but basically once you've loaded the model in, you go File, Open your STL model, and then you can click Slice, and then it will tell you how much it would weighs, and by virtue of that you know the cost, as well as how much time it would take, given the layer height setting, which the default is 0.15 millimeter layer height. When you want to print in the DSC, we just because of the way we're currently set up physically, we can't let students directly print to the printers, but we have a web application that you could submit print jobs through, and then you can pay using your credit card for the cost of the material. And again, we charge 10 cents a gram. And these are the different settings that you can choose from. Infill, if you're at all in doubt, you should probably just leave them. But infill 10%, that's pretty normal. Scale 100%, layer height 0.2, which is a bit coarse. You might want to go to 0.15, but you just click on that download to get it. Again, I'd just leave supports on. If it doesn't need them, Cura won't add them. And then you check the material down here. PLA plus PVA, TPU95, and there is a PETG there that this is just an older version. And we can go over this more in detail in class. We offer our workshop badge for this. All you need to do is complete 2 of the projects and then submit the print job, and submitting the project just gives me a heads up that you're going to be submitting a print job, and then once you've submitted it, I'll issue the badge a day or 2 later. So it's hands-on time. If you have any questions, let me know, of course, but I'm looking forward to working with you face-to-face in the Digital Scholarship Commons here in the library. Take care. Bye-bye.